Good morning viewers, I am Dr.I.Jannathul Firthouse, Assistant Professor of Mathematics, A.D.M College for Women, Autonomous, Nagapattinam. In this module, I am going to present Operations Research. First of all, we are going to see Introduction to Operations Research. Operation research is the systematic and analytical approach to decision making and problem solving. OR is a branch of applied mathematics that uses techniques and statistics to arrive at optimal solutions to solve complex problems. It is typically concerned with determining the maximum profit, sale, output, crops, yield, risk, cost and time of some objective function. Definition of operations research. Operation research is the application of analytical methods designed to make the decision makers choose between various courses of actions available to accomplish specified objectives. Now we are going to see the history of operations research. There is no clear history that marks the birth of OR. It is generally accepted that the field originated in England during the World War II. Some say that Charles Babbage is the father of operations research because his research into the cost of transportation and sorting of mail led to England's University Penny's Post in 1840. Operations research is useful for solving resource allocation problems, inventory control problems, maintenance and replacement problems, sequencing and scheduling problems, assignment of jobs to applicants to maximize total profit or minimize total cost, transportation problems, shortest route problems like traveling sales person problems, marketing management problems, finance management problems, production planning and control problems. Linear programming problem, the introduction of linear programming problem. Linear programming problem deal with determining optimal allocations of limited resources to meet given objectives. The resources may be in the form of men, raw materials, market demand, money and machines, etc. The objective is usually maximizing profit, minimizing total cost, maximizing utility, etc. There are certain restrictions on the total amount of each resource available and on the quantity or quality of each product made. Definition of linear programming problem. A mathematical technique used to obtain an optimum solution in resource allocation problem such as production planning. When solving a problem using linear programming, the problem is pinned to a number of linear inequalities and then attempt is made to maximize or minimize the inputs. Requirements. These are all the requirements. There must be well-defined objective functions. There must be a constraint on the amount. There must be alternative course of action. The decision variables should be interrelated and non-negative. The resource must be limited in supply. Assumptions. Proportionality, additivity, continuity, certainty and finite choice. Application of linear programming. Business, industrial, military, economic, marketing and distribution. Properties of linear programming model. The following properties from the linear programming model. First one, the relationship among decision variables must be linear in nature. And the second one, a model must have an objective function. And the third one, resource constraints are essential. And the fourth one, a model must have a non-negative constraints. Formulation, how to formulate the linear programming problem. Formulation of linear programming problem. Formulation of linear programming is the representation of problems situation in a mathematical form. It involves well-defined decision variables with an objective function and set of constraints. Objective functions. The objective of the problem is identified and converted into a suitable objective function. The objective function represents the aim or goal of the system, that is the decision variables, which has to be determined from the problem. Generally, the objective in most cases will be either to maximize resource or profits or to minimize the cost or time. Constraints. When the availability of resources are in surplus, there will be no problem in making decisions. But in real life organization normally have scarce resources within which the job has to be performed in the most effective way. Therefore, problem situations are within confined limits in which the optimal solutions to the problem must be found. Next, the non-negative constraints. Negative values of physical quantities are impossible, like producing negative number of chairs, tables, etc. So, it is necessary to include the element of non-negativity as a constraint. Steps involved in the formulation of LPP. What are all the steps to be involved? The steps involved in the formation of linear programming problem are as follows. Step 1. Identify the unknown decision variables to determine and assign symbols to them. Step 2. Identify all the constraints in the problem and express them as linear equations or inequalities of decision variables. Step 3. Identify the objective or aim and represent it is also a linear function of decision variables. Step 4. Express the complete formulation of LPP as a general mathematical model. Mathematical formulation of LPP. If xj, j equal to 1, 2, 3, etc. up to n are the decision variables of the problem, and if the system is subject to m constraints, the general mathematical model can be written in the form optimize z equal to f of x1, x2, etc. up to xn. Subject to gi of x1, x2, etc. xn less than or equal to, greater than or equal to bi is called structural constraints, and x1, x2, x3, etc. up to xn greater than or equal to 0, that is called the non-negative restrictions or constraints. Problem based on formulation of LPP. Problem 1. Production allocation problem. A manufacturer products two types of models, M1 and M2. A manufacturer produces two types of models, M1 and M2. Each M1 model requires 4 hours of grinding and 2 hours of polishing. And whereas each M2 model requires 2 hours of grinding and 5 hours of polishing. The manufacturer has 2 grinders and 3 polishers. So each grinder works for 40 hours a week and each polisher works for 60 hours a week. Profit on an M1 model is rupees 3 and on M2 model is rupees 4. Whatever is produced in a week is sold in the market. How should the manufacturer allocate his production a week is sold in the market? How should the manufacturer allocate his production capacity to the 2 types of models so that he make the maximum profit in a week? That is the problem. The solution, the given problem is tabulated. Machines M1 and M2. So grinding X1 and polishing X2, grinding 4 hours for M1 machine and 2 hours for M2 machine. So polishing 2 hours for M1 machine and 5 hours for M2 machine. The profit of each model, M1 profit is rupees 3 and M2 model is rupees 4. So M1 machine grinding per week 40 hours and polishing per week 60 hours. So here is a real situation from an industry. The manufacturer can, if he so choose, produces only model M2, but then his grinders would be ideal and his profits may be maximum. This is only a guess to be definite. We must tell how many M1 models and how many M2 models should be produced per week in order that his profits may be maximum. So mathematical formulation we are going to see how to allocate. So decision variables, let x1 equal to number of units of M1 model and x2 equal to number of units of M2 model. So objective functions, the objective of the manufacturer is to be determine the number of M1 and M2 model as to maximize the total profit. So maximize the total profit is equal to 3x1 plus 4x2 because the M1 model profit 3 per week and M2 model for 4 per week. So maximize is equal to 3x1 plus 4x2, that is the objective functions. Next we are going to see the constraints. For grinding there is 2 grinding and polishing. So for grinding, since each M1 model requires 4 hours and each M2 model requires 2 hours, the total number of grinding hours needed per week is given by, so 4x1 plus 2x2. Similarly, for polishing, the total number of polishing hours needed per week is 2x1 plus 5x2. Further, since the manufacturer does not have more than 2 into 40 equal to 80 hours of grinding and 3 into 60 equal to 180 hours of polishing. The time constraints are 4x1 plus 2x2 less than or equal to 80 and 2x1 plus 5x2 less than or equal to 180. So, non-negative constraints, since the production of negative number of models is meaningless. So, we must have x1 greater than or equal to 0 and x2 greater than or equal to 0. Hence, the manufacturer's allocation problem can be put in the following mathematical form. Find two real numbers x1 and x2 such that 4x1 plus 2x2 less than or equal to 80, 2x1 plus 5x2 less than or equal to 180 and x1 greater than or equal to 0, x2 greater than or equal to 0. And for which the expressions objective function is equal to 3x1 plus 4x2. Problem 2. Universal Corporation manufactures two products P1 and P2. The profit per unit of the two product is rupees 50 and rupees 60 respectively. Both the products require processing in 3 machines. The following table indicates the available machine hours per week and the time required on each machine for 1 unit of P1 and P2. Formulate this product mix a problem in the linear programming form. So, machine 1, 2, 3, product P1 and P2. So, available time in machine hours per week 300, 509, 812. Profit rupees 50 and rupees 50 for P1 and rupees 60 for P2. So, the solution of this problem. So, let x1 and x2 be amounts manufactured of products P1 and P2 respectively. The objective here is to maximize the profit which is given by the linear function maximize z equal to 50x1 plus 60x2. Since 1 unit of product P1 requires 2 hours of processing in machine 1, while the corresponding requirement of P2 is 1 hour, the first constraints can be expressed as 2x1 plus x2 less than or equal to 300. Similarly, constraints corresponding to machine 2 and machine 3 are. So, 3x1 plus 4x2 less than or equal to 509, 4x1 plus 7x2 less than or equal to 812. So, in addition, there cannot be any negative production that may be stated algebraically as x1 greater than or equal to 0 and x2 greater than or equal to 0. That is, a variable that is also allowed to assume negative values is said to be unrestricted in sign. The problem can now be stated in the standard linear programming problem. So, maximize z equal to 50x1 plus 60x2. Subject to the constraint 2x1 plus x2 less than or equal to 300, 3x1 plus 4x2 less than or equal to 509, 4x1 plus 7x2 less than or equal to 812 and x1 greater than or equal to 0, x2 greater than or equal to 0. This procedure is commonly referred to as the formulation of the problem. Next, problem 3, diet problem. A person wants to decide the constituents of a diet which will fulfill his daily requirements of proteins, fats and carbohydrates at the minimum cost. The choice is to be made from 4 different types of foods. The yield per unit of these foods are given below. Food type 1, 2, 3, 4, number of foods, yield per unit, proteins, fats, carbohydrates, cost per unit in rupees 54, 49, 89, 75 and the minimum requirement is 900, 300 and 800. Formulate the linear programming model for the problem. Now, the formulation of LPP model, step 1, key decision is to determine the number of units of food type 1, 2, 3 and 4 to be used. So, let 3 units be x1, let 4 units be x1, x2, x3 and x4 respectively. Feasible alternatives or sets of values of xj where xj greater than 0, j equal to 1, 2, 3, 4. So, objective function. So, objective is to minimize the cost, that is, minimize z equal to 54x1 plus 49x2 plus 89x3 plus 75x4. So, step 5, the constraints are to be fulfillment of the duty requirements of the various constituents, that is, for proteins of 5x1 plus 6x2 plus 9x3 plus 3x4 greater than or equal to 900. For fats, x1 plus 4x2 plus 4x3 plus 5x4 greater than or equal to 300. For carbohydrates, a 3x1 plus 2x2 plus 6x3 plus 2x4 greater than or equal to 800. Thus, the LPP model is to determine the number of units of x1, x2, x3 and x4 that minimize the equation 2, that is 54x1 plus 49x2 plus 89x3 plus 75x4. Subject to the constraints, that is the equation 3, x1 plus 4x2 plus 4x3 plus 5x4 greater than or equal to 300 and the non-negative constraints of equation 1. Thank you.